One of the big challenges of the inclined plane is trying to prove to yourself that the vectors are pointed in the direction along the inclined plane and perpendicular to the inclined plane after you look at the original vectors, specifically the gravity vector. So when I draw the gravity vector, I like to draw it just like that between those 2 points on the incline, because it kind of helps us see the geometry that unfolds here. Now keep in mind, what we are doing is we are making this our x-axis and this our y-axis in this problem here. And so looking at the gravity vector exclusively without looking at any of the other vectors, it kind of helps us see geometrically what's going on here. Now there's two ways to kind of draw the x components and the y components here. Basically what I'm trying to do is I'm trying to take my vector and separate it into a component that way and a component that way. But it's going to be a lot easier to see it if I draw the y component like this and the x component over here. So it gives me that triangle that I'm looking for here. And essentially, if I drew that same triangle, let's say maybe just I'll draw it right here. It's pointed down. There's my original vector. This is f of g, but I want to get it into this vector and this vector. And this is f of gy, and this is f of gx. So we want those two vectors, and now it's just a geometry problem, or a right triangle trig problem. I'm going to assign this an angle of 30 degrees, and essentially we really want this angle right here, and I like the number 30 just because I've got a right angle right there, which tells me that this other angle, which I'll do in a different color right there, that's 60. Which means that this angle right here must also be 30, which is important because it tells us that the angle that we're looking for matches the angle of the incline. But keep in mind, this angle is with respect to the y-axis here. So when we're looking at this right triangle here, we've got O, A, and H. And what's going to end up happening is that it's going to be sine that gives you the x component and cosine that gives you the y component here. So what you do is if you were trying to solve for, let's say, FGX, you'd say sine theta equals A over H. And essentially, O over H. And essentially O is FGX. And H, your hypotenuse, is just f of g. And so if we rearrange this, we would get fg sine theta equals fgx. And I'll flip them around 180. Actually, make sure you can see that there. I'll flip them around 180, and then I would say fgx is equal to fg sine theta, but we know that f of g is mg, so f of gx is always equal to mg sine theta. That's something that once you prove it to yourself, you want to kind of memorize it and always keep that handy. Now, we would get the same thing by doing cosine, only that would give us the y component. So cosine theta would equal A over H. A is FGY, and H again is your original gravity vector. So then you get FG cosine theta equals FGY. And then let's just flip it around 180 and rewrite f of g as mg, so you get mg cosine theta there. And so there's your y component, and what you're going to find is that your y component typically matches your normal force, unless something crazy was happening, but I don't really expect us to kind of address those type of scenarios in this class. So, you know, I would say if you can draw this yourself and prove this to yourself, it's a big step in getting to you to understand that FGX is this value here and FGY is this value here, and what we've done is we've written them in terms of the angle of the incline.